I'm Steve Brown, the technical editor of Spectroscopy magazine, and I'm here today with Rohit Bhargava, professor in the Department of Bioengineering at the University of Illinois at Urbana-Champaign. He is also a faculty member in the Beckman Institute Bioimaging Science and Technology Group. Professor Bhargava, thank you for joining us today.
Thank you, Steve. Pleasure to be here.
In a recent paper, you mentioned that extracting information from spectroscopic imaging data sets is not a straightforward process of treating a spectrum from each pixel as an independent measurement comparable to a spectrum from a conventional spectrometer. Why is that the case?
To understand this, Steve, I think we have to think about how spectroscopy had been practiced. So traditionally, samples were homogeneous. There were liquids, perhaps in a cell or maybe a piece of polymer. And simple Beer's law was invoked to understand the concentration and relationship of that with the spectrum. And an absorbance measurement in those sort of traditional instruments involved light that was pretty much collimated. So it went through the sample at a right angle, and pretty much the entire light went through it at the sort of same angle. The only differences were if you used a slightly different substrate. If you used barium fluoride instead of calcium fluoride, you might have different reflectivity and different cutoffs in the spectral region. But the introduction of a sample into the light beam didn't really change things much except for the absorbance. And so people did realize that there were other things going on, and there has been some work looking at the effect of the substrate, namely reflectivity and multiple reflections between substrate and things like fringing that were well known. But these were relatively very small corrections. So for the most part, one could just put in a sample into the instrument, and what one would get out would be an absorption spectrum that was directly related to the chemistry because the sample was homogeneous. Today we're talking about imaging, and imaging only makes sense if the sample is heterogeneous. So naturally there are boundaries in the sample at which light scatters. It's not just the substrate from which light reflects back and gets transmitted anymore. One also now start thinking about refraction within the sample, about scattering from the sample. Scattering is really the key to this process. So scattering from a certain point in the sample can transmit light to pixels that it was not supposed to go to. Scattering can also send light out of the cone of collection for the beam. So the beam is really not just simply recorded as with or without the sample, and the only change being absorbance. Now one has to really start thinking of scattering. This has both an effect on the spectrum, because spectrally the scattering may not be uniform. In fact, it is not. And one has also to start thinking about differences in spatial fidelity that might arise from the scattering. So this is really the reason why things are so different now, and why one has to treat the entire recorded image as a data set rather than think about a spectrum from every pixel being a separate and independent identity.
I see. You mentioned in the paper that a trend may emerge toward the development of application-specific instrumentation as opposed to general-purpose instruments. Have you seen evidence that this possible trend is becoming a reality, and if so, what are the implications?
Let me address the implications first. So, as we just talked about a minute ago, one then really has to understand how the sample and spectrometer relationship stands and how those two act together to really understand the recorded data. So from the implication standpoint, I think if one were to start recovering chemistry-specific data from a heterogeneous sample, one really has to understand how the spectrometer interfaces with that type of sample. If you have a large enough market where a certain type of sample, let's say scattering sample like a tissue or breast tissue or prostate tissue, which are two things of interest in our lab, if you have those repeatedly, say in a clinical lab, and you're going to do those kind of samples, then perhaps you could design an instrument in which the scattering is known or minimized or somehow handled such that we get chemistry information really quickly. So that's the sort of implication and perhaps the driving force for this trend. The evidence is, I think, around us. Up until now, most imaging instruments or even most point mapping instruments in IR spectroscopy were pretty much the same, and they performed rather similar functions. So you could put your sample in and load it up. Either the beam would raster through, or you would collect a two-dimensional image, and pretty much the same performance, same sort of data were acquired with slight differences between manufacturers. But a few years ago, we started seeing, most notably with Smith's detection, or what is now Smith's detection, making an instrument perhaps for the first responders or those in the homeland security sort of area. And then people realized that perhaps even within the spectroscopy market, there might be some niche areas which can be addressed. For example, Bruker came out with a dedicated microscopy system not too long ago, just about last year. And so there are specific segments in this market in which if we focus, we can then make an instrument that outperforms any other instrument. But it only does a limited number of things. So it's not a general purpose instrument, but the things that it does really well. And this trend is also perhaps encouraged or promoted by other technologies coming on board. So our lab and others, for example, have used what we have now termed discrete frequency imaging as opposed to Fourier transform or continuous spectral imaging. So this has primarily been driven by, in our lab, we've developed these narrowband filters that can be developed cheaply, that can be manufactured easily, and that are fairly low cost. At the other side are quantum cascade lasers, which we've also used. And so in quantum cascade lasers or filters, you're not really measuring the entire spectrum. You could if you wanted to, but usually what you're interested in are just a few frequencies of interest. So this is quite opposed to sort of the Fourier transform model in which you measure the whole spectrum, whether you want it or not. That's what you actually get. The minute you start doing discrete frequency things, then the question arises, which frequencies should we look at? And that's where the use and the end use of the eventual instrument really come into play. So from a general purpose spectral recording device, what you might have is a very specific function spectrometer that might be based on a set of filters or a QCL within a certain range, for example, and that might drive future applications. So it's both the need as well as the technology evolving now that will make this trend possible.
Excellent. How has data interpretation in IR microscopy and imaging improved recently in terms of identifying relationships between structure and spectra?
Well, that's a great question because this is one of the most exciting areas in IR microscopy today, and rightly so. So we've always known, in fact, my first paper that we published in this field demonstrated that the real part of the refractive index has a tremendous influence on the spectral data that is recorded. So this was in 1998, and we sort of thought that, okay, it does have an influence, we understand that, but there are more important things to be done, making better instruments, showing IR imaging is useful in a variety of applications, and so on. And about 5 years ago, or more accurately, maybe 7 years ago, people started realizing again that scattering and real transport of light through a sample really influences the data that we acquire, and it actually also limits us in applications. And since then, there's been a lot of work done. The first few attempts were more sort of model-based, so we would treat every pixel independently. We would treat things as if there was a scattering center there, and that's the only effect on the system. Then almost 4 years ago, we actually came out with a comprehensive theory for IR microscopy. And this is in a series of papers in analytical chemistry since then. So what we've been doing over the years is taking this theory and applying it to very specific cases. And now we can, certainly for some objects that are well-defined and whose properties we know, we can predict what kind of spectra would result if a particular instrument was used. The same framework was recently used to explain why we get and what is the limit of information in high-definition IR imaging. So early in 2013, there's an applied spectroscopy paper from my group that lays out sort of the theoretical background and simulations to show what is the quality of image that we can potentially get with IR imaging. So it's not just an improvement in identifying the relationship between structure and spectra, it's also leading to better design of instruments. And that in turn then allows us to better perhaps understand structure and spectra. This sort of resonance between basic understanding, applications, and instrument design is really one of the more exciting things in the field now. And I hope this will be an exciting thing for some time to come.
Excellent. That's very interesting. What other trends in IR imaging do you think will become important in the near future?
So I think the important perhaps trends we're seeing is this emergence of many new components. So we've already got, we've seen advances on the source side, lasers, filters, even better sources, better interferometers. We've perhaps not yet seen the full potential of what can happen on the detection side. So certainly hardware advances, as always, will continue to remain important. One thing that has not been quite as much important in IR microscopy has been theory and algorithms. I think this trend will really become apparent now. Once we have now realized that we are limited in the information that we can extract from IR imaging data, unless we use some sort of correction. So pretty much all forms of data recording will require some sort of data processing that is based on some physics of the instrumentation of the background. So what we're really doing here is moving from just a basic passive data recording to more of a computed data recording paradigm. in which computation and hardware are sort of merged with each other in a way that is quite synergistic. Most certainly, applications are going to be a big trend. There have been many new ideas in my lab. Certainly, we've used IR imaging on seed grains, on forensic materials lately, and other things. Biomedical, as always, will continue to, I think, remain strong. In these three areas, these are sort of the major trends that are there. The one trend, though, that I have not yet seen much evidence for, but is likely to emerge, is this idea of total information. So not only spectral information and not only thinking of a pixel independently of others, but how do multiple pixels work with each other? How do different structures in the image relate to the same chemistry or relate to the same problem? So we've not really seen analytical algorithms go after the entire imaging data. We've often seen chemometric algorithms focused on spectral data on a per pixel basis. We've seen imaging extracted at a specific wave number, for example, but certainly looking at all dimensions of the information is likely to be a nice area in the future.
Professor Bhargava, thank you for talking to us today.
Thank you so much, Stephen. It's a pleasure.